Greetings, folks. Welcome. Before I start this video, I do want to address the elephant in the room, and that is, yes, I did get a haircut. And yes, I did it myself. Now, on with the show. When economists use regression analysis, we usually start from a model of how we think the world works. That's what we call a population regression model. For this population regression model, we believe that y, that's the dependent variable, equals beta subscript 0 plus beta subscript 1x, where x is an independent variable or an explanatory variable, plus epsilon. Unfortunately, we really never have access to an entire population, so instead we conduct regression analysis using information on a sample of data. So a sample regression model is y equals b subscript 0 hat plus b subscript 1 hat times x. Let's look at a specific application where I want to know the effect that studying has on a student's grade. So I believe that the way the world works is that if a student studies more, they get a higher grade. So my population regression model is grade equals beta subscript 0 plus beta subscript 1 times the amount of time you study plus epsilon. So epsilon is the error term, which recognizes there are lots of other things that might influence your grade other than how much you study. And beta 1 is a population parameter that tells us what will happen to our grade if we study an additional hour. And again, unfortunately, I don't have information on every single student that's out there, the population of all students. So instead, I can do this analysis using information on a sample. So my sample regression model is grade equals b subscript 0 hat plus b subscript 1 hat times the amount of time you study. When we use information from a sample to say something about a population, it's called statistical inference. And we can do inference using regression analysis. So again, we want to know the effect of studying on test grades for all students. So that's this regression population parameter, beta subscript 1. Unfortunately, we can't ask all students about how much they study in their grades. So we conduct analysis using a sample, and we get a regression estimate of b subscript 1 hat. Here's a scatter plot showing information for 40 students on how much time they spent studying and their test grade. So the test grade is a dependent variable shown on the y-axis. Hours studied is an explanatory variable shown on the x-axis. And the value for b subscript 1 hat from the regression model is 2.7322. In other words, for every additional hour spent studying, your grade goes up by about 2.73 points. Here's a second scatter plot showing information on a sample of a different 40 students. Once again, we find that the amount of time spent studying has a positive impact on your test grade. So here, the estimate for b subscript 1 hat is 3.0182. In other words, if you increase your studying by an hour, it lifts your grade by about 3 points, or a little over 3 percentage points. Here's a third scatter plot showing information on a different sample of 40 students. Once again, we find that there's a positive relationship, but this time the specific value for b subscript 1 hat is 2.6625. So from this sample, an additional hour studied increases your grade by about 2.66 percentage points. I'm going to stop with just 3 samples, but in reality, we could collect thousands upon thousands of random samples of 40 different college students to see the impact that time spent studying has on their test grade. And if we did that, we'd get thousands upon thousands of different values for b subscript 1 hat. And we could take all those values and we could put them in a histogram, and that would be called a sampling distribution. Of course, anytime we make a histogram, we want to think about its shape, center, and spread. As it turns out, the sampling distribution of b subscript 1 hat has the shape of a t-distribution, so it's symmetric, single-peaked, and bell-shaped. The center of this sampling distribution is beta subscript 1, which is the actual population parameter that tells us for all students the impact that studying has on their performance on a test. And the spread of this sampling distribution is its standard error. I'm going to use the notation S subscript B1, and this is calculated using computer software or econometric software. Here's a picture of the sampling distribution of b subscript 1 hat. And we've got 38 degrees of freedom, because you might remember we started from a sample size of 40. But if you have a regression model with one explanatory variable, you end up with n minus 2 degrees of freedom. As I mentioned a moment ago, the shape of this t-distribution is symmetric, single-peaked, and bell-shaped. The center of the distribution is beta subscript 1, which is a true population parameter. Think about the spread of this distribution. If you start from the center, which is indicated by beta subscript 1, and you move to the right, you've moved over one standard error, and that's indicated as beta subscript 1 just plus the standard error. If you move farther to the right, you can move two standard errors to the right, and that would be beta subscript 1 plus 2 times the standard error. Of course, if you moved into the left tail, if you start from beta subscript 1, you can move one standard error to the left, or you can move two standard errors below the mean, and that's shown as beta subscript 1 minus 2 times the standard error. If you had specific values for beta 1 and the standard error, you could actually replace these letters with numerical values.